Hello, I'm Adira, and I'm developing a phase field model for densification during a sintering process, and this is the final update. The problem with traditional modeling methods is that they are computationally very intensive, since they calculate the exact positions of interfaces. This makes them extremely sensitive to many parameters, and interfaces, such as you can see here, often need to be handled separately as special cases. Sintering is a particle processing method which involves many boundaries between particles, and is thus very complicated to model using traditional modeling methods. Sintering forms solid structures from particles. As you can see here, initially you have a large number of particles densely packed together. Over time, through heat, the particles begin to grow and fuse together, until eventually you have a solid mass composed of many grains with many boundaries and some voids, which create boundaries between a vapor phase as well. This is a very complex system and is very difficult to model using traditional modeling methods. Phase field modeling reduces the sensitivity and complexity of the model by not calculating the exact position of boundaries, and instead locating them at the gradient in an order parameter. This leads to diffuse boundaries rather than discrete boundaries. As you can see here, the fuzzy interface between the green and the brown phase is an example of a diffuse interface. It doesn't go sharply from green phase to brown phase, and instead there is some mixing in between the two at the boundary. Order parameters can be conserved or non-conserved. A conserved order parameter would be the total concentration of a system during spinodal decomposition, whereas a non-conserved order parameter might be the amount of solid during solidification. The algorithm of a phase field model is relatively simple. First, you initialize the matrix of order parameters at every point in space. Then you calculate the change in the order parameter at each point over the time step. Then you update the value of the order parameters at each point. And what I'm doing is then outputting an image file with colors dependent on the value of the order parameter. Then you go back and calculate the change in the order parameter at each point over the next time step, and continue until you have reached your end time. I began by building a simple model of solidification, using a single non-conserved order parameter, the amount of the solid phase in the system. A seed crystal, in blue, in a liquid initiates growth as the liquid cools. The interface between the solid and the liquid is not calculated explicitly, and is instead located at a gradient in the order parameter. This means that there is, again, a diffuse boundary, not a discrete boundary, making it mathematically less complicated. Then I developed a model of spinodal decomposition, again using C++. This uses a single conserved order parameter, the total concentration of the system. The spontaneous phase separation is driven by interfacial energy, here between the green phase and the brown phase, so that the separation goes faster initially and then slower as the phases become more separated. Again, the interface between the phases is not discrete and is not calculated explicitly. This makes this substantially easier to model than traditional modeling methods would require. I then began to develop a model of sintering, where larger crystals grow at the expense of smaller ones, and small ones can even be completely absorbed by larger crystals. However, the total amount of solid is conserved. That's the single conserved order parameter in this system. There are also 3 non-conserved order parameters, which is the green orientation of each particle. This allows us to see the distinction between each particle in the grain boundary. The difficulties presented here are in combining conserved and non-conserved order parameters and handling the much more complicated free energy functionals that result. Another problem, which I began working on next, is particle motion. During sintering, particles move due to surface and grain boundary energy. Using the modified free energy functionals from Biswas et al., it is mathematically fairly easy to add the force and velocity to the free energy functionals. However, it is substantially harder to code, and this has been presenting a number of difficulties that I have been struggling with. I successfully developed phase field models of solidification and spinodal decomposition, and have begun to develop an accurate model of sintering. Next, I would like to continue to develop this sintering model in order to properly include particle motion, which is going to involve working to properly integrate the motion into the code. Then I'd like to expand to more in-depth sintering models using more particles and more complex systems. And in order to do that, I'm going to need to refactor the code to handle more general cases, because currently the code is very rigidly written to only handle the system that we have set up, which does not make it easy to expand. I would like to thank the U.S. Department of Defense Army Research Lab for sponsoring this project. I'd also like to thank Texas A&M for organizing and running this O-REU. I'd also like to thank my mentor, Jeffrey Bullard, who has been a fantastic mentor this entire summer, and I have really appreciated it. Thank you.